This question sets the stage. It's asking us to think about how the bandwidth, think of it like the radius of a search circle, influences the outcome of the meanshift algorithm, a method used to group similar data points together. The algorithm looks for dense areas of data points and assigns those points to clusters. The bandwidth affects how large or small that search circle is, and consequently how many clusters are formed. A larger bandwidth means a wider search circle. Imagine a larger fishing net, it will catch more fish together. In this case, the algorithm groups more data points together because it considers a larger area around each data point. This leads to fewer, larger clusters because smaller, nearby clusters are combined. Smaller bandwidth indicates a tighter search circle. Think of a small fishing net, it'll only catch a few fish at a time. The algorithm is more sensitive to small, local variations in data density. This will result in more, smaller clusters because it will find more distinct areas of higher density. This can even uncover subclusters within what initially seemed like a single cluster. Bandwidth indirectly impacts the algorithm's runtime. But the relationship isn't simple. A smaller bandwidth might increase the number of iterations because the algorithm has to make more fine-grained adjustments before settling on cluster centers. However, it depends a lot on the specific dataset's structure, how spread out the data points are. The meanshift algorithm can estimate the bandwidth itself, but it's not a guarantee of the optimal value. Often, experimenting with different bandwidth values is needed to get the best results for a particular dataset. A lot depends on the actual data. So, while it can often find a starting point, manual adjustment might be needed to refine the clustering. These are the individual customer spending habits, represented by their annual income and average transaction value. Each customer's data forms a single point in a two-dimensional space where the axes are annual income and average transaction value. In the meanshift algorithm, the bandwidth is a crucial parameter that defines the radius of the kernel used in density estimation. It controls the sensitivity to local density peaks. A larger bandwidth considers a wider area around each data point when searching for dense regions, which determines cluster boundaries. A smaller bandwidth focuses on local density, identifying finer details in the data. Think of it like this. Imagine you're looking for clumps of sand on a beach. A large bandwidth means you look at a wider expanse of sand, ignoring small clusters, while a small bandwidth means you are looking at smaller regions. Thus you would probably find more, smaller clusters. This is a clustering algorithm in machine learning. It uses a kernel density estimation to find clusters in data. The algorithm iteratively moves data points toward regions of higher density until convergence, resulting in the identification of cluster centers. The bandwidth parameter plays a significant role in the algorithm's performance and the resulting number of clusters. The algorithm works by iteratively shifting data points towards areas of higher density, using a kernel, a weighting function, with a radius determined by the bandwidth. A larger bandwidth will lead to smoother density estimates and fewer, larger clusters. A smaller bandwidth will lead to more detailed estimates and potentially more, smaller clusters. This title introduces the topic, how the bandwidth parameter in the meanshift clustering algorithm affects the results. It sets the stage for understanding the role of this crucial parameter. This indicates that a question about the meanshift algorithm's bandwidth parameter will follow. Get ready to think about its influence on the clustering process. This sets the context. We're working with the scikit-learn library in Python and using its meanshift algorithm to cluster data points. It involves customer spending habits, annual income and average transaction value, as features for clustering. This is option A of a multiple-choice question, exploring the impact of a larger bandwidth on the number of resulting clusters. The larger the bandwidth, the broader the area considered for clustering, so fewer but larger clusters would result. We'll come back to this later. This is option B, the opposite scenario. A smaller bandwidth increases sensitivity to local density variations, hence more smaller clusters are formed. Think of it as a more fine-grained analysis. Option C discusses the impact of bandwidth on the convergence speed of the algorithm. While a smaller bandwidth might require more iterations due to increased sensitivity, it's not a strictly proportional relationship. This option claims that the optimal bandwidth is always determined automatically. This is generally not true, as optimal bandwidth is often data-dependent and needs manual tuning for the best results. This is a key misconception to be clear on. This section title suggests it will describe the influence of the bandwidth on the mean-shift clustering algorithm. Think of it as a guide on how this parameter impacts the results. This heading focuses on the effects of using a larger bandwidth value in the algorithm. It's highlighting that a larger bandwidth leads to fewer, larger clusters. It's merging similar smaller clusters. This describes the consequence of a larger bandwidth, a reduction in the total number of clusters, and an increase in the size of individual clusters. This section header shifts the focus to smaller bandwidth values and their influence on the clustering process. Consider the difference from the broader, larger bandwidth approach. This explains the result of a smaller bandwidth. More clusters are identified, and those clusters are generally smaller. The increased sensitivity might even reveal subclusters within what was previously considered a single cluster. This section title sets the stage. We're diving into the core concept: how the bandwidth parameter in the mean-shift algorithm impacts the clustering results. It's all about understanding how the size of the search radius affects which data points get grouped together. Get ready to explore. Here's the central question of our exploration. We'll uncover how the bandwidth, a key parameter in the mean-shift algorithm, influences the outcome of our clustering process. We're looking at the cause and effect of bandwidth on the number of clusters formed. Imagine a wider net. A larger bandwidth means a wider search area. The algorithm groups nearby data points more liberally, leading to fewer, larger, and potentially merged clusters. It's like gathering pebbles on the beach with a big bucket. You end up with fewer piles. Now imagine a tiny net. A smaller bandwidth focuses on smaller, localized dense areas. This leads to numerous clusters, even potentially splitting existing larger ones into smaller, distinct groups. Think of gathering the same pebbles with a tiny cup. You'll have many more piles. Each tiny pile represents a smaller, distinct cluster. The bandwidth affects the speed at which the algorithm settles on its final clusters. A smaller bandwidth might need more iterative steps, like trying many different combinations, to find stable clusters as it's looking for smaller, more precise patterns in the data. It's not a direct, guaranteed relationship, though. This statement is false. While mean-shift can try to guess the best bandwidth, it's not always perfect. Often, you need to experiment with different bandwidths to find the one that best suits your data and the patterns you're looking for. It's an iterative process.